So this question asks us for the power that's dissipated in the 1 ohm resistor, which is that one right there, and I'm going to solve it using mesh analysis. So to do that, I need to label my meshes. So let's call this I1, I2, and I3 as the meshes here. And then if I look at the structure of this circuit, I notice that I have here a current source which is shared between two meshes. So the current source is shared between two meshes. So therefore, need to use a supernode. So that's how we're going to solve it. I can also think a little bit strategically here. The answer that I'm seeking is the power in just this resistor. So it would be sufficient to solve for mesh current I3. Once I know the mesh current I3, then I can calculate the power using just simply P equals I squared R. R is 1, and the current is I3. So the answer that I seek is actually just I3 squared. So I can kind of keep this little fact in mind for later on. But let's go ahead and analyze this with a supernode. So looking first at the internal structure of this supernode and looking at this current source over here, I can see that at the current source, what I have is 2 amps is flowing, and that is equal to mesh current I2 minus mesh current I1. So just to arrange this in sort of standard form where I have my variables on the left-hand side, I'm just going to rearrange this equation. So I have minus I1 plus I2 is equal to 2. And so that will be my equation number 1. The next thing that I need to do is define the path of my supermesh. And so the way that I do that is I look at the two meshes that are contained within that supermesh. So those two meshes will be I1 and I2. And I draw a path that kind of goes around those two meshes. So for instance, I go along like this, kind of around these two meshes so that it fully encloses my current source. I'm just going to draw some arrows on it so that I know which way around I'm going to proceed when I do Kirchhoff's voltage law. So Kirchhoff's voltage law around the supermesh will look like this. I will have, let's choose a starting point. I might as well define a reference node and start from there. So KVL from here is going to be minus 10. I then will come up to the 2 ohm resistor at the very top. And so that will have a mesh current I1. Then there'll be the next 2 ohm resistor, and that resistor will have contributions due to mesh current I1 and also mesh current I3. Then there'll be another 2 ohm resistor, which will have a contribution due to I2 and also I3. And then I'm back to my starting point. A useful sanity check is to count how many terms you have and compare that to the number of elements in your circuit. So I see moving around this loop, I see 1, 2, 3, 4 circuit elements and 1, 2, 3, 4 terms in my equation. So that's nice. That's a good little quick check. I'm now going to just simplify this equation a little bit. So I'll take all of the terms involving I1. So that's going to be 4 times I1. Next, the terms involving I2, which is just plus 2 times I2. And then the terms involving I3, there will be a negative 2 and another negative 2, so that's a negative 4 I3. And I'll bring the 10 to the other side, so it equals to 10. And that will be equation number 2. And then there's one mesh that I have not yet analyzed, which is mesh current I3. So if I do KVL around mesh I3, then this is what I'll get. So I might as well start here in the bottom right corner, and I will get current 1 ohm, voltage 1 ohm times I3, so it's just 1 times I3, which is just I3. Then there'll be the 2 ohm resistor, which will have contribution due to I3 and also a contribution due to I2. Then there will be another 2 ohm resistor, which will have current I3 minus I1. And then finally the voltage source, which I approach from the negative side, so that'll be minus 6, is equal to 0. Let's simplify this equation a little bit. So I'll just order my variables, sort them. So that'll be a minus 2 times I1, a minus 2 times I2, and then my I3s will be plus 5 I3, and I'll bring the 6 to the other side, equals 6. And so that will be equation number 3. So I have system of equations, 3 equations, 3 unknowns. I can be a little strategic because I recall that my final answer, I actually only need to know I3, I only need to know one of the variables. So therefore a good method is Kramer's method. So I'm going to solve this with Kramer's method. So to do that, I need to express this as a matrix. Bear with me, as a matrix. So let's have a look at that. Basically, I read off the coefficients from my equations. So from equation 1, there's a minus 1, a plus 1, and a 0, which is multiplied into this vector, I1, I2, I3, and right-hand side for first equation is 2. Looking at equation 2, my coefficients are 4, 2, minus 4, and 10. And then for my last equation, they are minus 2, 5, and 6. Okay, so to solve this with Kramer's method, I need to first calculate the determinant of that matrix at the front. So by the way, just as a matter of notation, this is AX equals B, so A vector of coefficients, or matrix of coefficients, X is vector of unknown variables, and B is vector of constants. So AX equals B is my matrix system. So the determinant of A is as follows. If you're not quite sure how to do this, then go back and watch my video on solving simultaneous equations. So I will just write out what these little subdeterminants are. The next one is a 0, so then there'll be some stuff in here, I don't really care. To calculate this is minus 1 times the determinant of this, and I'm just going to pretty much type this straight into my calculator. So it is 2 times 5 minus 4 times minus 2, which is 2, minus 1 by, this is 4 times 5, minus 2 by 4 is 12, plus 0. Then this will give me a minus 2 and a minus 12, so this is minus 14. I also need to know the determinant of a new matrix. So because I want I3, the third variable, then my new matrix I'm going to call N3. It's the third variable that I'm seeking. And this is a matrix where I copy the columns of A except for the third column. So the third column I replace with my right-hand side with my B vector. So that was 2, 10, 6, like so. Then I can go and calculate what this determinant is going to be. So that is just 2, 10, minus 2, 6. minus 1 times determinant of 4, 10, minus 2, 6, plus 2 times the determinant of 4, 2, minus 2, minus 2. And this will be minus 1 times, this is 2 by 6, minus 2 times minus 10 times minus 2, this is 32, minus 1 times 4 times 6, minus 10 times minus 2, this is 44, and 2 times, so that is 4 times minus 2, minus 2 times minus 2 is minus 4. So I have negative 32, negative 44, and minus 8, which is negative 32 minus 44 minus 8 is 84, negative 84. Therefore, my third variable, which was I3, is determinant N3 divide determinant of A, so that's minus 84 divided by minus 14. So 84 divided by 14 is 6 amps. And so therefore the power that's dissipated in that 1 ohm resistor is just I squared R, so that's I3 squared times 1. So 6 sixes is 36 watts of power that is dissipated.